Hello, my name is Peter, and in this video I'm going to be going very briefly over my aerothermodynamics of propulsion systems project number 1, showing how the geometry, the mechanical systems, and the fluent simulation are developed for a converging diverging nozzle. So let's begin with this. Let's go over to the modeling system, and in Design Modeler I made a very simple converging and diverging nozzle. The measurements of note to keep in mind are that the incoming side has a characteristic length of 0.35 meters. My outlet, it has a size of 0.4, so slightly larger than the inlet, and the choke is smaller than both at 0.25 meters. Interestingly, I set up just an angle here at 810. This angle allows for these sides to automatically be generated based on what angle I like and what I felt necessary. In this experiment, we'll be using 195 degrees. That eventually solves out to show this is a 7.5 degree half angle diverging section. Next, we can move into mechanical, where we can show how the meshing is solved for the system. The mesh was solved using prime mesh. Prime mesh is my preferred method of solving these kind of systems with mostly default settings, except for the element size being set for 001. I find that setting prime mesh to these settings allows for not only the quickest solving, but also very strong quadrilateral solving in the middle. Having triangles can induce extra noise and cause extra issues. We can see especially here this tear along the diagonal here. Triangles, in my opinion, cause a little extra noise and can, although produce less elements, often produce more interesting results when you have a higher detail mesh like this. So this mesh was chosen to have such high detail so that we would have a better chance of seeing all the shocks and subsections of any part of the flow when moving through fluid. Now, while on the topic of fluent, let's get over there. And in fluent, our system is set up very simply as so. If we look here, we've got our inlet. This pressure inlet for this experiment, let's run our simulation at 150 kilopascals, an arbitrary value picked for this experiment. Our outlet is a pressure outlet set for 0 pascals, that's gauge pressure, so essentially atmospheric conditions. The models that we're using are simply just the energy model. The only other change that has happened is that the fluid for air has been correctly set as an ideal gas for its density and not constant. This allows it to be compressed in our system and when we're solving our calculations. So if we allow ANSYS to go and produce our simulation, we're going to run our flow for roughly 500 iterations, and we will go and have a running solution after this. The things to keep in mind is that, especially if this is the first time, you can see my numbers are starting from 500 as this is my second run. But if you are starting your simulation for the first time at step 0, these warnings about reversed flow on certain faces will only appear closer to the end of the simulation and are often the sign of a detached flow or a shock developing in the diverging section of the nozzle. Here it looks like we still have that shock developing, or more importantly, our flow is detaching. But now as the flow begins to slowly fill back out, we may see this value reappear and disappear as time continues. So with 150 iterations left, something to keep in mind is that once this is complete, we'll be going over some of the contours and a couple of the graphs to show how some of these values change through the nozzle and especially through the diverging section, as we can see what the throat to diverging section causes in this system. So let's let ANSYS solve through some of these graphs and get some of our contours completed here. Cool. So let's get right to the meat and potatoes here, and let's look right at Mach number. Interestingly, with our Mach number, we have a very strong, very clean input. And as we creep towards our center region here, we can see that our Mach number mainly stays below Mach 1, as is a converging nozzle, and the theoretical maximum would be Mach 1 right here along this line. As we can see, as once we cross over this barrier here, our velocity rapidly increases up all the way closer to Mach 2 and begins to move down the diverging section of the nozzle. Interestingly, we have this oblique developing here and here, and this gives a strong indication that A, a shock is developing here because the system is finally detaching because it is overexpanded. This diverging section is too large for this flow, and the flow is struggling to move through. Another issue is that due to the number of iterations and the change in flow, this could be the result of the flow not being solved all the way to the end, but this has actually moved inwards since the previous run, showing that there still may be more work to do or more iterations to run, and the flow may have been detached earlier in the flow here. Another interesting model to look at would be the speed of sound. This one in density will look very similar, as speed of sound is a function of the density in general, or is just a function of the speed of sound. And we can see again, very high speed of sound in the converging section as the particles are packed very densely, allowing for sound to travel much faster. And as we move through the diverging section, we see that speed of sound drop tremendously as the particles are spread further apart. We can look at that again with the density chart. You'll see this will look very similar, where the density is very highly packed and finely packed in the converging, but very separated in the diverging section. And we can get more of an understanding of what's going on with the pressure chart here, as the pressure seems to absolutely plummet as we get closer to these separation points where the flow separates off the walls, allowing for a backflow to come in from our outlet region. Another interesting graph is that we can go and look at the velocity in general, and we can get a very interesting, very similar understanding as what we did with our Mach number, except now we can see some other noise and distortion happening as the flow attempts to solve and come back in, as this has likely not reached a steady state just yet. So with that in mind, let's look at some of the XY plots for how this information looks as we move down the length of our flow here. Our Mach number, again, increases consistently, passes through that center shock, has a small oblique noise, like dampening area here. We can see that if we look at the contour for Mach number. Due to how sharp the corners are here, we can see these lines appear. And this little hump right here, this little portion here is that downwards decreasing hump that we see in this portion of the line. Another one we can look at that is also interesting is our pressure. And we can see that pressure rapidly decreasing, and our pressure increases again here because the flow is completely separated from the wall at this point, and we can see the pressure of the exterior environment. The velocity for the system looks very nice and clean, showing the nozzle's functioning properly, but again we can see this dip at the peak due to the fact that the flow is completely separated from the nozzle. And it looks like that will be the end of it for today. Again, this video has shown the modeling systems, the meshing systems, and all of the fluent materials necessary in producing a converging diverging nozzle. Thank you.